Question 1 is about the forces on a kite. If you look at the question, the key word in the question is that the kite is stationary. Now if it didn't say the kite was stationary, we wouldn't know that the forces were in equilibrium. But because it does say that it's stationary, that tells us, it's the clue, the question is going to be about equilibrium. So the first part of the question, show on the diagram how force F, this one, can be resolved into horizontal and vertical components. Don't particularly want to draw on the book, so here's one I prepared earlier. So show on the diagram how force F can be resolved into horizontal and vertical components. Now hopefully it's obvious what the question actually wants. It is actually pretty sloppy practice to mix up pictures that have vector arrows with pictures of real things. Because when we're dealing with vector arrows, distances represent, in this case, force. And you can't really have a picture where distance represents force that's also got pictures of real objects like kites where distance means distance. Anyway, let's not get too tied up with that. It's pretty obvious what it means. This force that's slanting, it must be going partly up and partly across. So to resolve it is to find the components. So we're drawing the components by completing a triangle. So there's the horizontal direction. How far does it go? Well, it goes as far as there. So this part which I'm going to draw in now must be the horizontal component. And the vertical component, well, F is acting at the middle of the kite, so let's draw both components at the middle of the kite. So the idea of components is finding two forces that would do the same job, and the job of F is to act at the middle of the kite, so let's draw the other component there as well. We get the length by coming across from F. So there we have the vertical component. Of course, if you wanted to find the size of the two components, we could find the size of the vertical component by taking this opposite side. And we could find the size of the horizontal component by taking this opposite side if we wanted to. But here we weren't asked to find the size just yet. We're supposed to be showing where those forces are acting. And of course they are both acting on the kite, so that's why I've drawn them there. Next part, the magnitude of the tension is 25 newtons. Calculate the horizontal component of the tension. You can see the tension is acting at an angle of 30 degrees. That means it's got a vertical component and it's also got a horizontal component. Now hopefully you'll know straight away that you've got two things to guess. You've got to guess the horizontal component and the vertical component. Hopefully you know that one of them will be t sine 30 degrees and the other will be t cos 30 degrees. Because that's what components always are. The question is, how do you know which one's which? After years of faffing around drawing triangles, I've come up with what I now reckon is the quickest way of doing it, the easiest way. Just look at the picture. If you're not familiar with the values of sine and cosine for 30 degrees, put it in your calculator. The sine of 30 degrees is 0.5. And the cosine of 30 degrees is 0.866. In other words, if the angle is 30 degrees, the small component is the one that's got sine in, and the big component is the one that's got cosine in. So we have a look at this. If this tension makes an angle of 30 degrees with the vertical, which is the biggest component? Does it act mainly downwards, or does it act mainly across? And if we decide that that force acts mainly downwards, then the big component will be the vertical component, and the small component will be the horizontal component. If on the other hand we thought that that force was pulling mainly to the left and only a little bit downwards, we'd go for the opposite components. So leave me to think about that one. Part C. Calculate the magnitude of the vertical component of F when the weight of the kite is 2.5 newtons. It's going all mathematical in its language. When the weight, that suggests the weight's going to change. Obviously it's not going to change. I think it means if the weight of the kite is 2.5 newtons. The weight of the kite is whatever it is. It doesn't change. So how do we do that? Well, we know the kite's in equilibrium. So we know that all the vertical forces on it must be in equilibrium, they must balance. So what are the vertical forces on it? Well, there's the vertical part of the tension in the string, which we've already calculated. And there's the weight, both those holding the kite down. What's holding the kite up must be the vertical component of F. So the vertical component of F must be equal to the weight plus the vertical component of the tension, whatever that comes to. Next thing you've got to find, and a slight difference in the wording. The previous one said calculate, because we had to do a calculation, didn't we? We had to add things together. Next part just says state the magnitude of the horizontal component of F. So that means you shouldn't need to work it out, it should already be there. And it should either be so obvious you can just write it down, or it should be something that you've already worked out. So if we ever think about this, for the horizontal component of F, the part of F, well, since F acts up and to the right, the horizontal component is the part of F acting to the right, but we know the kite is stationary, so it doesn't go to the right, so there must be some force that's pulling it to the left that will be equal. And have we already worked out what the force pulling to the left is? I think we have. So the force to the right must be equal to that. The last bit, hence calculate the magnitude of F. Well, if we already know the vertical component of F, and we know the horizontal component of F, then just undo what we did at the start of the question, add them together, and we can find F. And it just says the magnitude, so we don't need to find the angle, we just need to find a way of adding together those two components to find what that value is for the resultant. Question 2. A uniform heavy metal bar of weight 250 newtons suspended by two vertical wires. And it says that one's made of brass, the other's made of steel. And it gives you the cross-sectional area of each wire and the unstretched length of each wire. And the next thing it tells you, the Young modulus for the two materials. And it asks you to calculate the extension of the steel wire if the tension in it is 125 newtons. Well, if the bar weighs 250 newtons, you would expect that each wire would support 125. So, how do we do this question? Well, it's mentioned Young modulus, so hopefully it's got something to do with that. Hopefully we know what Young modulus means, but in case we didn't, we could always have a look in the data sheet. And on the data sheet it says Young modulus is tensile stress divided by tensile strain, which is FL over A times delta L. Personally, I much prefer learning Young modulus as being tensile stress divided by tensile strain, because if you use that formula, you're sort of bossing the ideas around. I don't like this. I think FL over A delta L is just a jumble of 4 letters. But since it's on the data sheet as this jumble of 4 letters, it's probably quicker to use that. So we know that Young modulus, which is given, is FL over A times delta L. And we're trying to find the extension. So there's the formula, E, although the data sheet doesn't give the symbol E. E is what we normally use for Young modulus. FL over A times delta L. Looking for the extension, well, hopefully we know that that's the force, that's the original length, that's the cross-sectional area, and what's left, delta L, the change in length. And of course extension just means change in length. So you can calculate what the extension by rearranging that formula. Because it's supported by wires of two different materials and one is stretchier than the other, then one wire will stretch more than the other. So if you've already worked out how far the steel wire stretches, I suppose you could go right back to the beginning if you wanted to and work out how far the brass wire would stretch. Do the same calculation, putting in the value for brass, and then when you know how far the steel stretches and how far the brass stretches, and get the difference.